All right, welcome to this explainer. Today we're looking right under the hood of large language models and really dissecting the architecture of sparse autoencoders. Look, if you're working in computer science, ML, or cybersecurity, you already know that while LLMs have achieved some truly staggering capabilities, they remain for the most part completely opaque systems. So today, we are prying open that black box.
Here's our roadmap for the day. First up, the polysemanticity bottleneck. Second, unpacking sparse autoencoders. Third, generating feature explanations. Fourth, SAs and AI safety. And finally, scaling and future frontiers. Let's get right into it.
Section 1. The polysemanticity bottleneck.
So let's think about the sheer scale of the problem here. Take a model like GPT-3. You've got 96 layers. During a forward pass, the model is constantly generating intermediate activations within and between each of these layers. When we look at the vectors passed between layers for each token, you're dealing with a 12,288 dimensional vector. It is literally just this massive, dense, totally opaque list of numbers. All the context the model needs to predict the next token is crammed in there. The fundamental question is, how on earth do we extract actual, human-understandable meaning from that soup of numbers?
Well, the first huge roadblock we hit is something called polysemanticity. Now, you might look at a single neuron in a standard neural network and expect it to represent a single clean concept. Actually, scratch that. Ideally, you'd hope it represents one clean concept. But nope, that is really not what happens. Because these neurons are multitasking across totally distinct contexts, like you might have one neuron firing for antibiotics and also firing for computer architecture. Individual neurons become highly unreliable if you're trying to map out the model's logic.
So why does this happen? It essentially all comes down to the superposition hypothesis. Think about it. LLMs are exposed to an unfathomable number of concepts in their training data, way more than the actual number of neurons they possess. To compensate for that, models use a linear combination of neurons to compress a massive number of features into a very tight mathematical bottleneck. They're basically assigning features to an overcomplete set of directions in the activation space rather than neatly dedicating one neuron to one feature.
Which brings us to our core goal here. We desperately need to transition away from these messy, entangled polysemantic neurons and move toward clean, disentangled monosemantic features. Basically, we want to find a way to map those dense representations into a new space where one feature equals one isolated, human-understandable concept. No more multitasking.
Moving on to Section 2. Unpacking sparse autoencoders.
To actually achieve this disentanglement, researchers deploy a specific unsupervised dictionary learning technique. Let's walk a forward pass through it. First off, we extract those dense intermediate activation vectors from the LLM. Then, we take that vector and push it through an encoder matrix, projecting it into a much higher dimensional space to create an overcomplete dictionary. Next, and honestly, this is the magic step, we apply a sparsity constraint, something like a ReLU activation function, to just brutally zero out almost all the negative values. Finally, the decoder steps in and tries to reconstruct the original dense representation from that new sparse vector.
Following this exact pipeline from sampling those residual streams or MLP sublayers on the input end to applying the tide-weight autoencoder, we end up with our output. It's a sparse feature dictionary where only a tiny handful of specific, interpretable features are active at any given moment. So instead of that opaque vector, we get distinct features we can actually put a label on. Like, oh, this specific feature reliably fires for words ending in ing, or this one's for chemistry terms. It's an absolute game changer.
Anthropic and other top researchers have this great analogy for it. They call it an MRI for ML models. And that hits the nail on the head. We are essentially trying to non-invasively peer inside the brain of the model to diagnose its thoughts during a forward pass. Notice I said non-invasively. We aren't tweaking the model's core weights here at all. We're just mapping its internal states so we can read them.
Now, to actually train this MRI, the sparse autoencoder relies on a very specific two-part loss function. First, you've got your reconstruction loss, usually mean squared error, which basically just forces the SAE to accurately rebuild the original input data. But here's the catch. Without the second part, the L1 sparsity penalty, the autoencoder would just learn the identity matrix. It would perfectly memorize the data, which tells us absolutely zero about the underlying features. The sparsity regularization is absolutely crucial because it forces the network to use only a tiny fraction of its neurons to reconstruct the input. That's what forces it to isolate the really distinct, critical features.
All right, Section 3. Generating feature explanations.
So, let's say we've successfully trained an SAE. Awesome. But now we might be staring at tens of millions of these sparse features. The next massive engineering headache? Figuring out what each of those isolated features actually means. Manual labeling at that scale is obviously impossible. So researchers leverage other LLMs as explainers to automate the whole shebang. They build these pipelines that feed the top activating sentences for a given feature right into an explainer LLM and just ask it to summarize the semantic pattern. The explainer might notice, for instance, that a certain feature always fires when discussing antibiotic resistance.
But, early on, these generated explanations were just way too broad. To tighten things up, researchers introduced a pretty rigorous tree-based refinement process utilizing what they call close negatives. The system takes the candidate explanation and evaluates it against sentences from the dataset that are semantically very similar, but crucially, don't actually trigger the feature. By throwing these close counterexamples at the hypothesis, the pipeline strictly falsifies the bad guesses. This forces the explainer model to use chain-of-thought prompting to zero in on a much sharper, more accurate explanation.
Let's shift gears a bit. Section 4. SAEs in AI safety.
Because we've got these monosemantic, interpretable features now, we can actually do way more than just observe. We can intervene. Think about RAG systems, retrieval augmented generation. SAE features can act as high-precision probes to catch hallucinations in real time. Or for toxicity, we can pinpoint the exact sparse features linked to toxic outputs and clamp them down. And this is wild. By intervening on specific sparse features during a forward pass, engineers can dynamically alter a model's behavior on the fly. You might have seen Anthropic's famous experiment where they clamped a specific feature to make the model obsessively talk about the Golden Gate Bridge. They did all of that without retraining a single underlying model weight.
But look, to keep things grounded and impartial, we absolutely have to acknowledge the pushback from the academic community. Researchers like Stephen Casper have rightly pointed out that, sure, mapping these features is a phenomenal technical achievement, but it's really just step one. Simply finding features doesn't magically guarantee a safer model and deployment. There's a very active debate right now about whether some of this interpretability research is leaning a bit too close to safety washing rather than building robust, practical guardrails that can actually withstand adversarial attacks. Which brings us to our final section, Section 5, Scaling and Future Frontiers.
As the base language models blow up from billions to trillions of parameters, that standard L1 penalty we talked about earlier, it starts hitting some really severe mathematical walls. One massive headache is shrinkage, or feature suppression, where the L1 penalty artificially squashes the true activation values. To bypass this, the frontier is shifting toward top K SAEs. Instead of an L1 penalty, top K uses a hard sparsity constraint. It literally just grabs the top K highest activations and aggressively zeroes out everything else. This completely avoids the shrinkage problem and makes the whole operation way more computationally efficient.
But honestly, even with top K optimizations, scaling this up is a monumental beast. Sure, we can optimize the sparse operations, but that initial dense encoder forward pass, the part where we project a massive 12,000 dimensional vector into an even more massive space of tens of millions of features, that is incredibly computationally expensive. And that leaves us with a pretty provocative final challenge. Solving this memory and compute bottleneck is the exact hurdle the field has to clear before we can truly map the minds of the next generation of frontier AI. So are we going to find a way to efficiently decode these trillion-parameter black boxes? Or are the models simply going to outpace our ability to understand them? Thanks for joining me on this explainer, and definitely keep questioning the algorithms.